Okay, this is the third video in the set of titration videos. And what we're going to do is look at the data that we have calculated and look at what the graph will look like. And realize when you do this experiment, you usually go from the graph to the unknown, not from the knowns to the pH. But this is what your graph will look like. So we'll set it up and set up our graph. On the x-axis, we'll have the milliliters of OH minus added. And on the y-axis, we'll have our pH. And the titration graph will look like this. It'll start above 1 because it's a weak acid, and it'll go up, step up, and it'll look like that. Now, this region right here is called the buffer region because a buffer is a solution that resists pH change. So even though we're adding strong base right here, our pH isn't changing very much. So what we're going to do is add in the landmarks that we calculated here. Now right here, this is at 2.87. And at that point, we just have our acid, acetic acid in water, jumps right on up into the buffer region. Here, now let's just keep going because when you're titrating, you don't know where that half equivalence point is going to be. You get to here, and this is where it steps up a lot. The pH changes a lot in the equivalence point region. If you're in calculus, you know that this point right here, that's the inflection point. So the inflection point in calculus is when the second derivative is equal to 0. My calculus teacher in high school, Dewey Nelson, would always say that this is where the soup bowl holds soup, so your curvature is positive. This is where your soup falls out of your soup bowl, so this is where your curvature is negative. And so if you would graph the curvature, it would go from positive to negative. So this is the inflection point, but it doesn't matter in chem, but what it does matter is at that point, that's our equivalence point. The equivalence point really has nothing to do with pH. The equivalence point is when the moles of the titrant is equal, or HA, or acetic acid, is equal to the moles of OH minus. So at this point is where you have your equivalence point. Now, once you graph that, you go back in your graph and you find halfway to the equivalence point. In this case, it's 25. So you're going to go back to this point right here at 12.5, and that's our half equivalence point. And the half equivalence point is where the pH is equal to the pKa. So we have 4.74. So you use your equivalence point to find your half equivalence point, which is 4.74 for acetic acid. At the equivalence point for a weak acid titrated with a strong base, you're going to have a pH greater than 7 because we have a weak base in solution. And when you're past the equivalence point, then this part of the graph would be the same for whether you're titrating a strong acid or a weaker acid. Now, I'm going to draw what it looks like if I had a strong acid on the same graph. So I'm going to change colors here. And so if I titrated, say, H plus acetic acid, or hydrochloric acid with OH minus to make water, the difference would be, first of all, there would be no buffer region because there's no equilibrium here. It would step up very gradually, but at the same point, well, that was really ugly, but at the same point, you'd have, oh, that's really ugly. I gotta fix that. I can't handle that. So let's do it again. Ooh, that wasn't as good. Well, whatever. It still has the same equivalence point. The point is, if you start with the same number of moles of a strong acid as a weak acid, you're going to have the same equivalence point, because equivalence point doesn't matter how strong your acid is. It only matters how much acid you have. Now, if you have a weaker acid than acetic acid, let's make this one blue. So blue will be, get rid of that now. blue is a weaker acid, you're going to start up higher, and your equivalence point region will be a smaller step. Sometimes it's actually hard to see. So this right here would be a weaker acid. But still have the same equivalence point. Okay, so those are the landmarks. Remembering here, let's put it back to black, right here. This right here is what's called the buffer region. And you do all sorts of different problems with buffers. And remember, in the buffer region, I usually use Henderson-Hasselbalch because what you have in the buffer region is a solution that contains both the weak acid, in this case, acetic acid, plus its conjugate base. So it contains both the weak acid and its conjugate, and that's what causes a buffer to happen. Okay, I think we're done with that. And then the next video, we're just going to walk through what happens if we titrated a weak base with a strong acid.